Hello, everyone. We are Team 19102. We worked on the Biosphere's wave generator. The members of this team are
Hi, I'm Ali Al-Khunaisi, and I'm a mechanical engineer.
Jojo Mills, Electrical and Computer Engineering.
Martin Rojo, System Engineering.
Cody Petrick, Mechanical Engineering.
Rachel Siedenberg, Electrical and Computer Engineering.
Titan Tran, Mechanical Engineering.
Hello, this is Martin, and I'll be going over this slide. The Biosphere 2 Ocean is looking for an upgrade to the vacuum wave generator installed in 1980 when the Biosphere 2 was first built. The wave generator is the key piece of equipment that is a part of the life support system that helps circulate water to ensure the system is well mixed and there is no stratification. The Biosphere 2 is trying to breed and manipulate coral to be more resilient and as the Earth's climate changes. Coral acts like the tree in the forest and plays an important role in the ocean's ecosystem. Yet, almost half of the world's coral has been lost. Our goal is to provide adequate schematics of upgrades to gates, actuators, and coding to simulate the actual environments of the ocean to improve the reliability of the system with maintenance. Our scope of work does not include any changes or work to the existing motors, blowers, or associated piping.
When approaching the problem, our focus was to satisfy the customer's requirements and enhance the system's efficiency and reliability without making major changes. The only analysis we had to perform was a stress analysis for the gate material to show that the new material has an insignificant deflection. The project was divided into sub-problems depending on our majors to ensure that everyone focuses on their work. There are three major system requirements in our project. The first one states the minimum of the modulus of elasticity for the gate material we choose, and this was verified by choosing Delrin as our gate material. The second is to let the operator know if the actuator stalls, whether due to actuator issues or gate issues. The third one is to let the operator know if the float tilt switch inside the trough is activated so an action can be made.
Hi, this is now Titan speaking. When looking to choose our gate material, actuators, and sensors, our focus was to make sure it was reliable, automatic, replaceable, and have a fail-safe operation. We used peep charts to determine the specific parts we were going to use for our design. We then listed the pros and cons of each chosen part to get an idea of what our limits were. Out of the pneumatic, electric, and hydraulic actuators, our best option was the electric actuator. When choosing our material for the gate, the trait factors were its coefficient of friction and its durability, proving Delrin to be our most reliable option. We decided a float tilt switch was going to be our best option for the water level detection due to its accuracy. Looking at our requirement verification table, our 5 main requirements were its operation environment, safety requirements, design features, and the interface requirements, each with their own sub-requirements. Listed in each column was its limit reference value, our measured value, and if we passed or failed. These are the rest of the requirement verifications that fall under interface requirements. The reason for why the pass-fail column is still TBD is because we were not able to finish testing due to COVID interruptions.
Hello, my name is Rachel Siedenberg, and I'll be talking about the results for our project. To start off, for our project, we wanted to design new gates because the current gates are worn down and sometimes deflect. So we chose Delrin as the new gate material because it is deflection resistant, has a low friction coefficient, and has low moisture absorption. We also ran analysis on this material and saw that the maximum deflection the gate would have is 0.0009 inches. We also need to choose an electric actuator that can be ran constantly, have a high enough IP rating so that it will not be damaged by water, and have enough force to move the gate. We chose the XLR FT45 because of its IP rating, 51, and its long estimated lifetime. As a safety precaution, we added a sensor to the design that would be attached at the top of the trough. Once the sensor is activated, the actuators will open the gate to flush out the water from the trough, and a notification will be sent to the GUI alerting the operator of the error. We chose the LV600 as our float tilt switch because of its simplicity. It only has an on and an off mode, and also because of its durability. We also developed code for the controller that automatically runs the actuators and detects if an actuator stalls or if the sensor is activated. If any errors were to occur, then an alert is sent to the GUI to notify the operator. The interface takes in 3 values: the current vacuum pressure, how many troughs are open, and the desired height of water in the trough. And those values control the actuator movement.
Hi, this is JoJo Mills, and I will talk about our deliverables. Our project has 4 deliverables: the GUI code, the actuator code, the assembly and part drawings, and a troubleshooting guide. We have created a graphical user interface which asks the user for 3 inputs that are then sent to the controller. It is a very simple design, but due to licensing issues, we were unable to get a screenshot. We also have written code for the actuator movement, but with the restrictions from COVID-19, we were unable to test the code due to an inability to access testing facilities. Next, we have a troubleshooting guide, which will be a set of guidelines to help the Biosphere team with the updated system in case something goes wrong and what steps they should take to fix an error in the system. Lastly, we have compiled a set of assembly and part drawings detailing the actuator and gate and how they are assembled together, along with a drawing of the system as a whole. This assembly part drawing of the gate and actuator is an example of one of the drawings we will include in our deliverables. The gate and actuator were our main components of focus. And then due to the scope of our project, it was more focused on the proposed design, so we do not have any demonstration photos or videos on the working system. We were planning on demonstrating the actuator movement with the code at design day, but because of COVID-19, we can no longer do this.
This is Cody Petrick. I'm going to talk about surprises, lessons learned, problems we overcame, safety, and the environment. Some of our surprises were realizing that the original system description we received from the Biosphere was inaccurate. The system was originally designed for use with electrical actuators instead of the pneumatic actuators currently in use. The troughs of the wave wall are all connected via piping and are not independent from each other. And lastly, learning from fluid dynamics professors at the university that research needs to be done before we could mathematically model the flow of fluid in this system. A couple of lessons learned were to always verify information if possible, and that site visits are an effective way to get information quickly. Our problems we overcame include limited access to the existing wave wall components because it is mostly buried, limited access to construction documents of the wave wall with uncertainty of what drawings were just proposals and what drawings accurately depict what is currently buried at the Biosphere. And finally, limited access to seats and licensing provided by a third-party contractor of the Biosphere required to write code and build a GUI. For safety concerns, we implemented a float tilt switch to cut power to the blower motor in the case of high water levels in the trough. This is to prevent water from being sucked up. The environment is inside the Biosphere 2's ocean biome, which is essentially outside on a beach. There is no chance of rain, but the gates and actuators will be exposed to high humidity and possibly fine dirt. These components will never contact any water during routine use. The actuator selected has an IP rating of 51 to withstand these conditions.